So I'll talk about the use of affine-correspondences for the tasks of rectification, auto-calibration, and scene parsing. And these will, this is single view geometry. So what we do is to use constraints from repetitive textures, coplanar repetitive textures to generate the constraints we need to recover this geometry. So the talk is just one image is all it takes, and this was a CVPR tutorial talk that I'll be giving here. So I just wanted to quickly recognize the people who were on these papers. These are my co-authors from this work. And the work that's being presented spans several papers that you'll see. So just an outline of the talk. Just to motivate the interest in the work, we'll show some applications. And then we'll talk about how to get the measurements that are needed to generate the constraints for the geometry we want to estimate. So this is, remember again, a single view. So this is a single image input. So we'll talk about the representation needed to do this. The third is just a review of camera geometry. So the idea is that we'll need some concepts from single view geometry and the real projective plane to motivate the next section, which is the solvers. And the solvers will be what we use to recover the geometry that we're interested in particular for rectification, for partial calibration, for lens undistortion. Even for the absolute orientation of the camera with respect to the scene, well, we'll do that as well later on. That ties into number 5, which is, while the talk is mainly focused on using affine correspondences to generate these constraints and to recover the geometry, it's possible to use these other features to combine, for example, imaged scene lines to estimate geometry with the affine correspondences. So the idea is that if you have different scene content, some scenes have more texture, some have more straight lines in the scene, so you might want to leverage that, and we'll talk about how to do that. 6 will be limitations. So in fact, affine correspondences aren't really used in practice. There's been thousands and thousands of citations generated, tens of thousands, but no one uses them. The question is why? And this is true not only in single view geometry, which is ill-posed and difficult, but also multi-view geometry. In fact, I think Thomas has a paper on that. Even they tried to get affine correspondences to work in multi-view geometry, and they had to take into consideration many things, including uncertainty. And so we'll talk about why this is the case and what is it possible to fix it. Then I'll talk about prior work, and the idea is that once we have all the concepts introduced in this tutorial, then we can revisit what came before, and you'll understand what those works are about, and then Q&A. So we're in single view geometry, and so we need constraints to sort of recover the geometry. So what can we use? Well, one thing to use is coplanar repetitive texture, and the idea is that it's everywhere, especially in urban environments, but not even. And there's different sorts of constraints that they generate. You have different types of repetitive textures. You have symmetries. It could be translational. It could be reflection. You have rigid transforms or isometries in the scene plane that you can use. So there's many different transformations and how things map onto each other. And the idea is that when you're imaging these translations or these reflections or whatever, of course, after the imaging process, they're not. There's a distortion and warp that is involved there. And the idea is we can sort of restore the invariants that are associated with different levels of calibration or rectification equivalently. So, you know, if and the idea is that if you have a pattern in the scene, a repetitive coplanar texture, then you know that depending on the pattern type, that certain invariants must hold. And then you estimate the geometry necessary to restore those invariants. So that's the first step, is to write down the equations and encode the invariants in a clever way. The second step, of course, is minimal solving, or it doesn't have to be minimal, but we do it for combinatoric sake. So you solve and recover those, the geometry needed to restore those invariants. And then you have it. You have the geometry, you've restored the invariants, and you've removed some ambiguity from the imaging process. And so these are these are examples. Now, these are all rectilinear cameras with very little distortion. And so, you know, these are what we consider easy now. And we can even remove lens distortion with the methods I will present. So, and the underlying assumption for all the work with affine-covariant regions is that coplanar repeats are related by isometries, which includes symmetries, of course. So one application is rectification. So you have an input image, and you want to compute a metric rectification, for example. So you can see, for example, on the left, all these three images have a tremendous amount of barrel distortion, some even nearly fisheye. And the quality of rectifications that we can get from these methods is quite high. If you look on the left image, for example, the top left image, there's actually three of these discs. There's, I guess it's a hexagon in the front and a circle in the middle, but in the very back, you can even see the third pattern, where in the original image, in my opinion, it's impossible to see. The same goes on the bottom. Like, you can see that oblique image of facades. And on the right, we've rectified it. And even at first glance, the distortion is so large, it's not really possible to see which side of the street it is. It's the left side. But you can see much more. You can removing this distortion allows you to reason about the scene. And that's one idea. Another idea is gravity direction, right? If you know the horizon line, and at least in partially calibrated camera, you have an uncalibrated gravity direction. You know where the horizon line is. You know where the ground plane is. It's defined by it. So here I show the horizon line that's estimated by our methods. So it's a circular arc, and the reason for that is that it's the image of the vanishing line, or the ground plane horizon line. And in this particular model that we're using, which is introduced, I call the division model, lines image as circular arcs. And you can see, of course, that in both of these images, at least in the traditional sense, okay, you have an interior of a building, but you don't really see the horizon, like where the sky meets the ground. It's sort of just gotten from the infrastructure. One other thing to mention, what's very impressive about these results, at least in my opinion, both of these results, well, they can be gotten by many of the solvers that will be presented here, but this result is possible with only one affine-covariant correspondence. So that vanishing line estimate, the circular arc, can be gotten by one affine correspondence. So in a ransack type approach, it can be very effective if you can do exhaustively, basically. So of course we have gravity direction. Well, then we can also do the rectification. I mean, the gravity direction, or the horizon line or vanishing line, only gives you a fine rectification and undistortion, but then you can use the other constraints in the image to get your metric rectification. And that's what's shown here. So there's also for segmentation and symmetry detection. So you have patterns in the scene, and you want to understand where those repetitive structures are. This is very useful in scene understanding. Repetitive structures cause all kinds of problems in matching, two-view matching especially. And the idea is that we would like to leverage that rather than have it be a liability. So on the left, you see some affine-covariant extractions. And what can you do with this? Well, you can use this to segment the scene. So we can use this as a unsupervised training to detect the pattern in the scene and get actually a pixel level segmentation from local features. So we have a very coarse sort of understanding of where the pattern is from the affine covariant regions. And then we use that in a training way to do in an unsupervised way to do a pixel level segmentation of the pattern. And here you see a couple of different types of patterns already that we're capable of doing. The left is a rotational symmetry. The right is a wallpaper pattern. It's a symmetry group, finite. And then on the bottom are isometries, rigid transforms. So this is sort of representing some of the things that are possible. And one thing I like to point out is that, okay, I think we got lucky actually, but if you look at the mosaic on the top left and the segmentation has a hole in the middle. And that's because the symmetry from the affine covariant regions is an 8-fold symmetry, but in the middle it's a 5-fold, it's a pentagon. So it actually was accurate enough to recognize the difference, or we just got lucky. So one of the two. Again, with this facade example, now I have two views, and stereo matching. I mean, Thomas has a very famous paper with others on this wide baseline stereo matching problem from local features, but even this is sort of a different modality or different level of problem where you have lots of lens distortion, extremely oblique views. So can you actually stereo match these guys? And from local features, I would say no, not without some tricks. So the idea is that we can use our solvers to actually produce these orthophotos. And the idea is that, well, can you actually see some of these structures in the original image? I would challenge you on the left images to find where that white building is that is in the blue box that is matched. And in fact, if you look, I think the easiest one to see it is on the second input on the lower left. You can see a little white sliver on the left side. That's where that white building is, that is stereo matched by these blue boxes. So you can see that there's a lot of image content there that's sort of hidden in this viewpoint after it's been rectified by our algorithms. So the question is, how could we use this? Although we're not currently state of the art is not really leveraging these types of ideas, but is it possible to use this very nice capability to solve these types of problems? Another application, auto-calibration and scene parsing. So the idea is that you want to recover basically the entire intrinsics of the camera. Focal length, principal point, lens distortion. I mean, of course, there are more. There are some simplifying assumptions that are made, but let's say that's enough to get you pretty close to what the calibration is. And you can do this, and this goes with the complementary features and affine covariant regions and image parallel scene lines. So the idea here is that you can jointly estimate the absolute orientation of the camera with respect to a coordinate frame in the scene, established by the dominant textures and scene lines, and then also jointly estimate the camera intrinsics, because you have certain additional constraints on the image of the absolute conic. This is very powerful also for scene parsing, because the vanishing points and vanishing lines of the scene. In particular, 3 orthogonal ones if you have a Manhattan frame, which is the assumption used here. So that's what the labeling is. So the vanishing point labeling is labeling the image parallel scene lines that are converging at the vanishing points, red, green, and blue. And vanishing line labeling, which is for the affine, on the right, you see the affine covariant regions labeled. Now, what's interesting about that is you're using both vanishing points and vanishing lines for the scene parsing here. Why? Because in the affine covariant regions, it's in a lattice, or in particular, like just a grid. And of course, there's many vanishing points along the vanishing line where those affine covariant regions are translational symmetries. So that's why we label them with vanishing lines. All vanishing points along that vanishing line are consistent with, not all, but there's a set of vanishing points along that vanishing line that are consistent with translational symmetries in the plane for those affine covariant regions. And then, of course, if you have this information, you can get very accurate rectifications, which is shown, and undistortions, which is shown on the bottom. Bottom is like a cutout of the undistortion. And then you have the two rectified planes of the building. So how to get, first off, like we need a representation of the scene. How to get the measurements of that we need to do these types of things. And that's what this section will be about. So first off, let's have some mathematical definition of what is a coplanar repeat, because at least for when we're using affine-covariant regions, this is the concept that we will be working with. And what I've defined here is an image rigid transform. And the image rigid transform will be the sort of geometric verification of this is a repeat. And what it is sort of a composite function of a distorted point. And you have a distorted point, and you have the function f, which is undistortion, or it could be back projection if you were more general. A lot of the formulations in the presentation, although not all of them, can be equivalent for an undistortion or back projection function. So you have the undistorted point, and then you have this homography, which is this planar transformation in the image, which relates correspondences. And then you have the distortion or projection function, which takes you back into the image. So you undistort, back project, you transform by a homography, which also encodes the isometry, and then you image again. And if those things are in perfect correspondence, then you have a coplanar repeat. And in general, we want regions that are corresponded this way. And what I show on the right are rectified patches. In fact, these are rectified by the algorithms presented in this presentation. And you can see that once that you remove all of these distortions in the plane, that you can see the repetitive structure there that is, in this case, related by translation. And what remains is, after you plug this translation in and you the correspondence in the scene plane, you can then sort of model the entire process of the image rigid transform. In fact, we won't be doing that, and I'll explain why when we do the solver design, but this is how we define a coplanar repeat. And of course, we relax this definition to include noise, imaging noise, for computer vision applications. It's not so rigid, no pun intended. So what do we do? Well, we need measurements to sort of identify what is repetitive texture. So we need to first find salient regions that could be candidates for repetitive texture. In particular, we use the maximum, like one of the ones we use is what's called an MSCR detector, which you see, and this is just an extremal region between high intensity and low intensity areas, this contour. And then from that, we extract differential geometry. It could be the first moment, which is the cross, or like curvature extrema, which are these two dots and the orange dots on the left side. And we construct a frame, this affine basis, essentially. So the representation of the feature becomes this affine basis in this construction. This affine basis has a particular property, which is affine-covariance, which is where the name of the feature comes from. And the idea is that of affine-covariance is that if you affinely warp the image, the affine basis will warp with it, or the feature detection on the left side. So the features are warping with the transformation. An affine is a pretty general transformation, and locally it approximates even a homography. So this is a nice property to have, and it's something that we need because we need to encode or observe the geometry changes. And then there's this description process where these affine bases, the patch local to the affine basis is the affine basis is normalized to a canonical frame, which removes the distortion locally, and this patch is somehow embedded. It can be embedded by SIFT. It can be embedded by a neural network. We don't care. It's agnostic to us. But that's sort of the process of the encoding. And here you also see reflections. So We've detected some translational symmetries and their reflections. And reflections are typically encoded by a trick, which is to just flip the image and do the detection again and then encode. So what is the input to our algorithm look like? Well, it's what we call an affine-covariant scene. So of course, the algorithm doesn't see this, it sees this and this. And that's what really the representation is of the algorithm. In particular, for most, but not all of the solvers that will be presented in this presentation, we use what I call the point parameterization of the affine-covariant feature, which is just, it's very easy. This is just when your detections are described by this affine transformation, which relates the canonical basis on the right to points in the image, the x1, x2, and x3. And this is really what the representations are used, and these are homogeneous. So we're using 3 vectors here. For in the image space, it would be the Euclidean coordinates would be x, y, and the homogeneous coordinate is 1. So that is our measurements that are defined by the affine-covariant feature. There's other works that use a different representation. In fact, Thomas and I are exploring the use of a different representation of the affine-covariant region now for something that was work in progress. So why use affine-covariant regions versus points? Why not just use points or Harris coordinates, for example? Because they will, of course, detect on symmetries as well. Well, one of the issues is you need good correspondences. So if you look at the image on the left, it's full of trash, many different detections on texture, and the actual symmetries on the right, which are, if I show what's been filtered on the right after the estimation, the actual good features on this texture are quite few. And so, having the affine-covariant region gives you immediately 3-point correspondences that are consistent with some symmetry. And if you try to do that independently for different point correspondences, it's much more difficult. So having a region corresponded gives you much more information, just the point, and you get that for free. Well, there is some cost, but you get it. And it reduces your search basically for the types of geometry that we need. Also, some of the solvers that will present, it's not enough to have just point correspondence. We need region correspondences. And here I show some motivating example here, which is in the perspective image. You have regions corresponded in the perspective image, and there these corresponded regions shown by these simple geometry figures don't have equal area. Because of the perspective warp. But we know that an invariant of a affine rectified space is that these must have equal area in the affine rectified space, those things that are repetitive or related by an isometry. So we need a measurement not on a point, but on a region, because we need to measure area or scale. And the idea is that we will use our solvers to restore this invariant of equal area. And the geometry will be recovered during that restoration process. Why not SIFs, which are SIFs are similarity covariant, and the idea is that for some of these solvers, SIFs could be appropriate. It depends on what you're trying to recover. But we get this extra level of covariance with, which will be important, which is the affine covariance of the affine covariant regions. So what do we need to do now? Well, we have the detections, as I described. We have these affine bases, and somehow we need to establish where the repetitive texture is. Well, this is once you have this embedding, once you've done the description and the embedding as I described before, you can just use some clustering algorithm. I've played with many. It turns out that for this type of problem, single link agglomerate clustering is quite effective. So that's what we use. But again, it's choose your favorite if it works well. It probably depends on the embedding that you're using as well, what works the best. And then what you get is not correspondences, as is typical for two-view geometry, where you have pairs of points that you relate, but you have corresponded sets. So you have a set of affine-covariant regions that are related. And now you have something to play with. You have geometry and you have them clustered, and now you can start playing with constraints. This is the correspondence pipeline, just as an overview from everything we talked about. So you have on the left your detections, you have your parameterization, which we use this point parameterization for the most part. And then you do the descriptor clustering and you get these tentative coplanar repeats. Now these are tentative, meaning they don't necessarily satisfy our definition of a coplanar repeat before, but it just gives us this appearance clustering that we can now we can later verify those when we actually try to solve the scene. So now some camera geometry. We'll need some concepts from single view geometry to understand the solvers. We're all familiar with this, which is a pinhole camera. We have a matrix, a 3x4 matrix that represents a change of basis between the coordinate system in the world and the coordinate system of the camera. And it's relating a world point X to an image point, a point in the image plane. Let's call it small x. It turns out that we have a simplifying assumption, which of course we have points, our points are planar, at least our affine covariant regions. So we can simplify the geometry a bit and work with homographies instead of camera matrices. So we recognize that if we make a nice choice of coordinate system, which is that the plane is actually the plane z equals 0, the third column of the camera matrix is annihilated by all points in the plane. And then we can represent our cameras by homographies with a unfortunate abuse of a notation. Many people complain that I use P's here instead of H's for homographies, but let's just go with it. So, so now you have, we're not in the, we're in the real projective plane. So all our points live in the real projective plane now. So we have our scene points, our image points, everything is represented by embedded in R3. But we have some additional problems. We don't have, we're not, once we introduce lens distortion, we're not in the real projective plane anymore. We have this type of distortion, and it's something that, of course, is more common now, especially with GoPros. So you get a lot of this barrel distortion, which is shown on this GoPro Hero 4 wide image. And so we need to include this in our model. And just to show you what the effects are of these animations is showing you once you do the undistortion, then you basically can create a rectilinear image. And you can do this for cameras that have fields of view less than 180 or significantly less than 180. You can undistort the image. Actually, a lot of these solvers can handle cameras with larger than 180-degree field of view, but then you can't, of course, rectify undistort the image. You can undistort only a cutout. So the rectification solvers that we will design are often remember, we're restoring invariance, and we're dealing in the real projective plane to construct these constraints. But if we don't model this lens undistortion or lens distortion, in fact, then we're going to get a bias model. So we don't want that, or it's just going to fail completely. And one question is, like, there's often a criticism of minimal solvers, but also why we use them, is why can't you just recover later? And I'll talk about that in a second. Meaning, why can't you assume that you have mostly rectilinear camera and then back it out later? And that can be done via a nonlinear estimation, for example, local optimization, via Leavenberg Marquette or whatever, and just throw that extra terms in there and try to recover it later. And I'm going to explain why later, but you can think of one thing as spatial verification, right? If you are in a ransack routine and you're estimating some geometry, you want to see the consensus set. How consistent is this geometry with my measurements, which is what the consensus set is measuring. And if you have a biased estimate of your geometry, then your consensus set is going to be much smaller than it actually should be. And furthermore, you won't recover from it, because when you go into local optimization, you want to use only those measurements that you think are consistent with your geometry to sort of get a refined measurement. And you will only be sampling a small part of the image with that. And I'll show you an example of that later. By the way, if there's any questions, just stop me. So we need a model for radial lens distortion. Actually, we use radial lens undistortion. And this is most minimal solvers use the division model. There's many reasons for it. One is it's very friendly to minimal solvers because it's an undistortion model. So it takes you into the real projected plane, and you can immediately start measuring. You can immediately start designing constraints there, versus, for example, a distortion model to model it. And I'll talk about why working in the image space is problematic in a few slides. But the division model is, I show its geometry on the left. So you have an image point, which is this x tilde, distorted point. And you have some function, quadratic function, this 1 plus lambda r squared. And it's only a 1 parameter model, so it's quite friendly for minimal solvers because it's only one unknown. And the image point is orthographically projected onto this curve, which is defined by the division model. And then back projected is the ray, which is the undistortion of it. Or it's not, you can consider yourself now, quote, in the real projective plane and start doing your constraints there, which is this, I call a pinhole point in this figure. Yes. Sure.
Is there is no problem with determining the center?
There is. Yes, so absolutely. And one example is, like, the most common example is in the internet, people crop their images. So of course this changes the center of distortion or center of projection. And this is a very good point, and something that I should have mentioned here. These are radial models. So you assume a radial symmetry here. And of course, if your center of projection or center of distortion is displaced, you've now violated this radial assumption, of course. And so what we typically do in this work, although that changes in some work I've done afterwards, but in the model, and some of the simplifying assumptions that we do for these solvers is we assume the center of projection or distortion is coincident with the principal point, which is in the center of the image. So all of these things are aligned. So we make many simplifying assumptions. So when I say that we, quote, partially calibrate or auto-calibrate, it includes many of these assumptions that are there. And yeah, so these, and it's also a good point on notation, which is that the x tilde squared and y tilde squared that you see in the equation there is center subtracted. So this is a radius. So yeah, I sort of glossed over that, and I should have said that in the previous slide. But here you can see also that a nice thing about these back projection models, in particular this, and in general, like a generalization of the division model, just a rational function. You can have numerators and denominators with polynomials that can model more complicated curves. It turns out this model is quite effective, though, for bootstrapping things. And you can see in the figure on the left that you can model fields of view greater than 180. The curve goes below the image plane, or the plane parallel to the image plane, the x-axis. So it models, and on the right we show an example of that. You have a lens with a greater than 180-degree field of view, and we're able to reasonably undistort a cutout of it on the lower left or on the bottom row. So just to give you an idea of what some single view geometry looks like in terms of restoring these constraints. So here on the left is like a distorted image of a chessboard with some vanishing points and some translational symmetries or conjugate translations equivalently under the division model. because the division model is, well, it's not technically invertible. It's easy, right? It's a quadratic equation. We can find the roots easily in the plausible one, and we can also distort quite easily with it. So going both ways is not a big problem. So I'm showing the distorted image on the left under the division model, and although it's an undistortion model, and on the right, I show its geometry, and when you restore it, this is what things look like. And so this is our goal when we use a division model, is to get in the scenario where we're dealing with the real projective plane entities that we can use there, coincidence of vanishing points, etc. Here I show a little more intuition about some geometry of RP2 that we're interested in. I mean, this is going to be relevant for the conjugate translation solvers, but just to give some ideas. We have an image plane, and we have some lines in the image that are parallel in that image plane. So like some railroad tracks or something like this, or sorry, I'm not in the image plane, but in the scene. So the three lines are parallel, could be some railroad tracks, for example. And in the image plane, they of course converge at a vanishing point. And on the left, we have the Gaussian sphere, which is which we construct the vanishing point on the Gaussian sphere. That what we do is we look at the interpretation planes of those that go through the images of those 3D lines, and we look at the normals of those interpretation planes. And if we cross the normals, those normals will lie along a great circle. And if we cross those normals, which can be done by SVD, or if you have many of them, or just taking the cross product, you can construct the vanishing point. Then once you have the vanishing points, if you cross again, you get the vanishing line. So this is a very elegant and simple geometry that's being shown here. And on the right, I show what happens to the vanishing point. The image of it, once it's distorted, it sort of gets, by a lens, gets distorted to the image point. The sphere is to remove essentially the homogeneity of the real projective plane. Well, a couple things. It's basically makes the real projective plane unique, right? We restrict everything to have norm one.
So we draw their image plane, so this somehow relates to the camera. Does the sphere relate to the camera?
No, this is just a sphere. It's just a sphere.
For what reason is it there?
Well, we noticed, for example, that these normals trace out a great circle on any sphere that's centered. The focal point has to be the center of the sphere, and so like we noticed that, for example, great circles represent parallel scene lines in the image
When you say focal point has to be a center, well,
of the sphere.
I choose the sphere so that its center is the focal point.
That's right. Yes. You're wondering what the point of the sphere is.
Yeah,
Well, I mean, well, as I said, like, for one thing, you're dealing with homogeneous quantities. So this is a visualization of these homogeneous quantities and says that they're unique. We've chosen one representative. They happen to have norm one, okay? And then we notice some nice geometry, which is that vanishing points, that parallel lines form great circles on the sphere, for example.
This is just a model of features.
That's right, yeah,
So it's a sphere with antipodal point.
yes.
It's just a visualization.
Yeah. I didn't mean to make it too fancy, but it's particularly elegant for showing the vanishing point and vanishing line geometry because, you know, circles on the sphere are corresponding. And you can see also like these other great circles that the vanishing point is intersecting where those great circles intersect. So on the Gaussian sphere. Okay, just a note, why do we want to undistort and go into the real projective plane? Instead of like, why not just say, I have a point in the image and I have another point in the image. Let's model, like in 2-view we would do, for example. Why not just model region to region or model point to point? Why not directly encode these relations instead of worrying about, you know, because you can write those equations down, of course. Why worry about this other stuff? Well, one thing is, if we look on the equation at the bottom right, we have the undistortion function f, or a back projection. We have the image transformation, the image isometry, and we have the distortion projection function, the distortion function, and then we have projection. So The idea is that the x tilde is related by this pi of gamma x tilde prime. That's the relation you would need to encode, and it's really nonlinear. So because you have to do this, eventually you have to do this casting rays into points. And then also, we don't know that we have, depending on your distortion and undistortion function, you're not guaranteed that they're analytic functions. They can be more complicated if you have higher order distortion functions. So one direction may have to be iterative, not closed form. I mean, even with the quadratic, you get two roots. And then you have to, as I said, project rays to image space. So this tends to complicate things when you do these operations. So what you would like to do is just go one way and work in the real projective plane. That's how these solvers are typically designed. And you sidestep some of these more complicated issues than working in the image space directly. So now we introduce some of our minimal solvers for these problems. And as I was sort of motivating before, when we go through this process, the idea is that these first batch of solvers will be rectifying solvers, and the process of rectification is essentially reversing the imaging process. We have an image of an object, and we want to get as close as it looks like in the scene. And this is a process where we progressively remove imaging distortions, which is basically traversing the rectification hierarchy. So on the left side, you see our equation for a camera viewing a scene plane, which we introduced before. And this transformation P can be inverted and then decomposed. And in particular, it can be decomposed into a projectivity, an affinity, and a similarity. And basically, we can remove the projective distortions, and we can remove the affine distortions, and we can get within a rigid transform, a similarity actually, of the scene plane. So that's with the constraints that I'm going to introduce, that's as far as we can go. So the first step is to do the affine rectification, which is estimating this first quantity. And invariants are restored there, parallel scene lines, equal scale of coplanar repeats are two examples. Then we can remove the affine distortion. So ratios of angles and extents of lines are congruence is restored. And that's as far as we can go with the type of constraints that we'll introduce, because we can't recover the rest of that ambiguity. We don't have constraints available for us just from image measurements alone. You would have to have some additional annotation. So what a lot of the work presented in this tutorial was novel, and I wanted to sort of motivate how we can get there. So on the top row, we have, if we have, for example, translations in the scene or reflections, these types of transformations, then we can get all the way to a semi-metric rectification. And in particular, the state of the art before the work that we did, if you had an undistorted image, a rectilinear image, you could get to the affine rectification through this. But what we propose with these minimal problems is to jointly get to the affine rectification, which I will motivate again in a second. I did a little motivation before, but why to do this jointly? What's the motivation for minimal solvers? We'll talk about in a second. So now we can go from a fisheye image or from a distorted image all the way to the affine rectification. And then we take another step using additional constraints and solvers, which I'll introduce, which will get us to semi-metric. If you have isometries or rotational symmetries, you again we go to affine rectification, and then through some proposed work we had, we can get to the metric rectification by restoring the congruence, this invariant of extents of the optics, the blue stars as well. It means that there is a scale ambiguity in one direction. So you have, you basically can stretch it in one way. Yeah, typically along the reflection axis. Is there a better term for it? Maybe I use semi-metric, but yeah.
Well, metric preserves distance.
Well, it's you careful there. It's up to scale. It's up to scale. So the entire image can be it's sort of an abuse in my terms of terminology, but when multi-view geometry, the Blue Bible talks about metric rectification, they really mean up to similarity, ambiguity. So a scale, a rotation, and a translation.
Well, yes, but I mean the metric between 2 points in actual the plane that you're recovering is true.
Yes.
Since the distances are I mean up to
Yes.
Unfortunate, except it's unfortunate. They call it metric, but metric is not precise.
But
Distances are not precise. And the metric is-
congruence is restored.
at least part of both metric.
You can, sure. Up to scale, yes. Up to scale.
Yeah, I wasn't going to start a movement to change the terminology. So
So semi-metric is standard.
no, that's my invention, but metric is standard.
Metric is standard.
Semi-metric, we had to come up with some name for it. So I had some animations here that I could have used. So again, like, why go through this trouble of the proposed? We've talked about it a little bit, but I wanted to actually show you some real results from this particular example. So the blue box represents a hierarchical approach or a graduated approach, where we start with the state-of-the-art solvers, assuming that the image is rectilinear, try to enforce the constraint of equal area, and that in the affine rectified space, these repetitive structures have equal area. And then in a nonlinear refinement, so you sample some measurements, you propose some geometry, and in the nonlinear refinement, we introduce the lens distortion and try to recover that from those measurements that are consistent with the minimal sample or whatever was sampled by Ransack. On the bottom is when our proposals are joint for both affine rectification and lens undistortion, the division model parameter essentially, which I introduced earlier. And you can see in this is anecdotal, but you can see in this case that we're unable to recover the correct rectification qualitatively. And the reason is because, exactly as I say, is that you don't know the consensus set. The proposals are too bad to get a good set of inliers or measurements that span the entire image. And you need to observe the lens distortion. You need to observe the geometry. And you're unable to recover from that because the distortion is too great. So this is really the motivation for the proposed work. And also in general, I think the motivation for minimal solvers, which is you need to have some solid polynomial systems to try to get basically to recover a good consensus set so that you can refine it later. So it's a lot of work to design these solvers typically, but it's worth it, is sort of the message. Well, how do we measure what a good rectification is? It's actually not straightforward, because essentially what we want to do is and I'm going to explain this equation a bit, which is to remember I was speaking about this rectification can be seen as reversing the imaging process and as a way of undoing the imaging process up to as little ambiguity between the image and the scene as possible, the scene plane. And so to do warp error, if you have some ground truth gotten by, who knows, but you have some ground truth in Oracle, the idea is that we pre-image, we do our rectification, we undo the imaging, and then we image with the ground truth. So we sort of use our estimate to undo the imaging, and then we re-image with the ground truth. And then we look at the discrepancy between these two to understand how bad or how good our rectification or estimate of camera geometry is. And one comment on this is that, remember, depending on your level of rectification, you have an ambiguity. So actually, when you're estimating your warp error, you have an estimation problem because you have to estimate this ambiguity and sort of not marginalize isn't the best word for it, but sort of estimate it out of this forward and backward process, or backward and forward process, and then you get your warp error. And so this is what we call the warp error, this process. And I wanted to show for a particular example of increasing undistortion parameter estimation error. So this is this division model parameter that as you increase the error of lens undistortion, you can see how the discrepancy in this process is increasing. And you can see that for a very small perturbation of the lens undistortion, how bad your correspondences get on this chessboard, which are the green and red dots. I don't know, can you see them okay there on the right? And this is motivating if you have a fixed threshold and if you ignore the lens undistortion parameter when you're minimally solving in RANSAC. If you have a fixed threshold for correspondences, you will see in this image on the right that there's only a small region that will be inliers because of this threshold that you choose. But on the extents, the green and red are far away, and you will not pick up those measurements, and you will not capture the geometry as observing it across the entire chessboard. So what is the first solvers that we did? They're called conjugate translations, which are, this is the rectilinear case. I'm showing these rhinos. This is actually, it's a print of Andy Warhol. It's in the Pittsburgh airport. On the left, these are some conjugate translations. This is the rectilinear case, which was solved by Shafalitsky and all. And the idea is that you have an image of a pinhole image of a translational symmetries or wallpaper or frieze pattern on a scene plane. And why is it called a conjugate translation? Well, it's because of the form of the transformation. You have this P, which is the homography, as we discussed before. It's not a camera matrix in this case, it's a 3x3 matrix because you're viewing a scene plane. You have the homogeneous translation matrix and this P inverse. And this PP inverse is what motivates their name conjugate. This is the form of this transformation. And you also have an additional constraint that the vanishing point and vanishing line must be coincident, which is this L transpose U equals 0. Yeah, so this is the geometry that we're relating these point correspondences, this xk and xk prime, for example. These are the correspondences that we'll use, the measurements that we'll use to introduce constraints. A little more detail about this. Now our work was radially distorted conjugate translations, and the idea is here now that we have now a distorted camera, and we have to introduce. We have to model this distortion, and now you see how the geometry changes under distortion on the right. You've seen it before. The vanishing line becomes a circular arc, as well as the lines that are joined from the point correspondences. The conjugate translation is measured by this undistortion, this conjugate translation, and then this distortion. That's a radially distorted conjugate translation. As I said before, though, we wouldn't work in the real projective plane. So what we do is we undistort those points. So we're given distorted points. That's our measurements gotten from either point from like corner detector or from like affine-covariant regions. We use affine-covariant regions for the reasons I described before. We undistort them with the division model of lens undistortion. And you can write out all the equations and the constraints. And this gives you, after some manipulation, gives you a system of polynomial equations. There were some tricks that had to be done here. There was some false solutions when we wrote down the system and tried to manipulate it, and so we had to saturate it. And in the end, though, we used Grosvenor basis to solve problems of this type. I wanted to talk a little bit about the types of measurements that we solve for. So what I'm showing in the top left are the types of point correspondences, or the affine-covariant point correspondences given by the point parameterization of the affine-covariant regions that we can solve for. So the first one is the most obvious, is a translational symmetry, but we can, well, because we have some additional constraints available to us in terms of, we have more measurements than, fewer constraints and measurements, we can relax, and we can actually let one point sort of vary along the translation direction in terms of scale. So this would be like for point correspondences or affine covariant regions. If you have SIFs, those are on the right, we can solve for these two direction solvers. You have two different translation directions. And this is when I draw these are on the scene plane, these point correspondences with pre-imaging. And you have two different directions. And then even we have where in one direction you can have a scale varying, which is what's showing on the 4. What else do I want to say about this? This is just a review of the unknowns of the problem. So you have the vanishing line, which is an unknown on the constraints, the vanishing point. The scale is the magnitude of translation. If you have if one of the points is translated in a different magnitude, it's that relative scale. Lambda is the division model of lens and distortion. So these are the unknowns that you have to solve for in the system of polynomial equations that is generated. And so those systems are sort of concisely written there at the bottom. And I show at the bottom, on the bottom right, some example undistortions and rectifications that are gotten by the solver. And in this case, again, it's impressive to me that you can get this nice rectification on the bottom right. For example, the number 1 in the minimal configuration on the top left, that's one covariant region. So you only need one measurement. So in a sense, you can exhaustively sample your correspondence space, which is important because these things are noisy and the geometry is badly conditioned. Now we go to a different solver. So this was the journal extension from that paper, or the journal version of it. And we came up with a different solver, which it very much simplifies the solver. In fact, it's analytic, or closed form you can call it, because it's a univariate quartic that it results in, rather than doing this Grobner basis. And the idea is that we're using meets of join points. So what is a join? Well, a join is these black lines that are so this is in the distorted scene. So we actually have distorted meets and joins that are shown here. So bear with me there. But a join is simply like joining 2 points, and then a meet is where all of those lines are meeting. And the joins give you the parallel lines, and the meets give you the vanishing points, and then you join again to get the vanishing line. So it's the algebra that you will see is the join of meets of joins. And that's what's shown here. I think I lost a join. Oh no, I'm sorry. We didn't actually join. That's right, because the vanishing line is left as an unknown, so you don't have to do that final join. So you only in terms of generating the constraint, it's just meets of joins. And so in the scene plane, on the scene plane on the left, you have the correspondent points that you're joining. This is pre-imaging. So the colors are the extents of those things that are parallel, that are in correspondence. And then this is an affine-covariant region in the scene plane. So this is like one of our measurements, and you can see how many constraints it gives you. It gives you lots of constraints to play with. And then if we show the projection by P, so the pinhole projection, you see the vanishing points and vanishing line that is generated by this geometry. And then if we distort it, which you get the distorted geometry, which is the circular arcs that are converging at the distorted vanishing points and vanishing lines. And so you just write these equations down, right? We start in the undistorted real projective plane, and then we express those points in the real projective plane by their undistorted functions, the division model. We apply those to the distorted points to get the undistorted points. And then what happens is you get this equation at the bottom, which is on the left is your constraint matrix, and on the right is the unknown vanishing line. And we know that these vanishing points must be coincident with the vanishing line, so we must be 0. And hence this constraint matrix on the left, which is it's a function of lambda. And we know it must be singular because you have, for non-trivial solution, you have this that the determinant is 0. So once you have you know that the determinant is 0, we just take those equations, compute the determinant, and you get a univariate function in lambda, which is a quartic. And now you can recover lambda by solving a quartic rather than the Grobner basis. And once you have lambda, you back substitute, you get L, and that's linear. So it's quite a simple solver, a couple of microseconds. And one correspondence to get the kind of results you see at the bottom. Again, So this solver you'll see later is much more stable. It gives extremely good results. It's extremely simple to code. No fancy Grosvenor basis, which is nice when you can avoid it. In fact, it's even faster. It's half a microsecond, which is extremely fast in C. There's a few details about this. Like, in fact, you have so many constraints that you actually could recover additional parameters, right? You could recover a second lens distortion parameter, for example, because this problem is over constrained. You don't want to do that because these measurements are too noisy. So we do something, we use this abundance of measurements to select the best solution in the minimal solver. So what we do is we sort of, we sample, and then we use those constraints that we don't use as a verification in a small part of the ransack component, to really just kind of find out how can we get the best minimal solution from this affine correspondence. And we use the remaining points as a consistency check.
So is lambda here an unknown?
Lambda, like in this case, it's a good question because I have this, so comparing only L and lambda are unknown here.
Only lambda.
And L, the vanishing line L and lambda are unknown. Everything else can be constructed from generative.
I don't understand how do we get from the scene to the undistorted image if lambda is unknown.
We recover, so which way are we going from? Because when I'm showing in the top row, I'm showing the imaging process. But when we run the algorithm, we actually start on the right and go left. We start with the measurements on the right, which are gotten from our distorted affine-covariant regions. We plug them in, we plug those into the constraint equation on the bottom. Those tildes are our distorted points gotten from the right side of this image. So I should probably change this figure a bit. You plug those in, you just compute the determinant, solve for lambda, and then solve for L, basically.
Of course, F is the inverse of FD. So this is
Yeah, so F, yeah, so close to the inverse. You have to solve a quadratic and choose the right root. F is the radial lens undistortion function, which is the function I introduced earlier. Maybe you weren't here for that part, I'm not sure. FD is the inverse of it, quote unquote. So in it, you solve a quadratic to solve the inverse. Choose the best root.
So this is matrix 3 by 3. No?
So the vanishing line is you have so you have 3 constraints for, let me see, hold on one second. Reddit notification. Sorry, you have it's determinant of a 3 by 3, yes. So, and you need it to be ranked efficient because you want this null space to be of the vanishing line.
In lambda, the determinant of the matrix.
Be careful though, because there's some cross products in there. So that's increasing the degree of lambda as well.
So multiply first.
So you cross and then you cross again. So these are skew symmetric matrices, right? This notation is this is skew symmetric product.
Okay, so elements of the 3 by 3 matrix are some polynomials in lambda of degree
4. Yes.
And when I take the determinant,
No. After you take the determinant, it's degree 4.
okay, but the elements of the 3 by 3 matrix are elements in lambda, polynomials in lambda of what degree?
Lambda is, well, when you write down the lens undistortion function, it's of degree 1. It's just lambda, r squared. And then you start taking cross products, and then you have to take the determinant. So I don't know the exact structure.
It's a code. Well, it's expected that 4 must be divisible by 4.
somehow does.
Okay.
Yeah.
No, no.
But if the 3 by 3 matrix and all is
So the idea is that if we look at in terms of choosing how to design the solver, you have the left versus the right. So these are the different constraints that were used, and it can show you that just sort of that clever constraint design it matters. The same sort of geometry is being modeled, but two different ways of generating it. And on the left side, it requires Grosvenor basis. The elimination template isn't that big; it's 14 by 18 still. And then on the right side, it's as I said, a quartic, and then a linear solution for L. So now we go into affine rectification by restoring equal scales. The idea is that in the affine rectified space, so I have this function h, which is a function of the distorted points and the vanishing line again, and the division model of lens undistortion parameter. If we apply that, then we know that these triangles, that the area of these triangles and squares and its hexagons are equal. So this is an invariant that we can use to encode a solver, to design a solver. And our unknowns in this case are again L and lambda, similar to the prior meets of joins solver. So before we were talking about point correspondences, but now we have correspondence sets. And the idea is that our correspondences, our constraints are generated by a set. So for example, we can have 2, 2, 2, which is like these different colors encode our affine-covariant regions, which are in correspondence, the green, the red, the blue. We can have 3, 2, which is the green and the red, of course, and 4. So these repetitive structures, which are this texture that's being extracted, these are the minimal configurations that we'll be dealing with for these solvers. These are what generate the minimal number of constraints for what we want to solve for. So how to encode this equal scale constraint? Well, you have your rectifying transformation, so let's write it out. In this case, it's this affine rectification can be achieved with this matrix, which has the vanishing line in the third row. And then you have your lens undistortion function. So it's just basically you have your lens undistortion and then your affine rectification, and then you generate your rectified points. If we have an affine covariant region, one of these triplet of points, then we apply that rectifying transform to the basis. And the determinant of those points, then, if we put those into a matrix, is the scale of that particular affine covariant region. And we set these scales equal to each other. We know that they must be equal to each other in affine rectified space. So we write down these equations, we set them equal, and this generates our constraints. And now we know that those affine covariant regions must after these transformation by this must be equiscalar. And yes.
So what do we mean by X underline?
X underline is the affine rectified point.
Okay.
X bar is or underline is the underbar is the affine rectified point. X tilde is the distorted point in the image space.
Okay. And the last coordinate of X underline is 1.
Yes, because you have alpha there. So you can assume that the first two coordinates are Euclidean and the last one is 1.
And it must be 1 for this to be true.
Well, you have the homogeneous scalar there. So yes, it must be 1 in this case if you have this non-zero scalar.
We cannot just take any representative. It must be this canonical one.
Yes. But X bar, this is computed. So like I don't understand your question though. So in X tilde I, those are your measurements. So that's the Euclidean points and 1. And then I'm just writing out the transformation, and we don't know, we don't know there's an unknown scale factor there, right? So, and it falls out, right? Because if you, yeah, so what is your question then?
Yeah, the question is just, is the last element in X under bar is 1?
That's right, it is, yes. So, so these solvers, we couldn't do much with them. So, meaning to simplify these constraints. And so essentially what we did was we plugged it into a solver generator. They turned out to be unstable because they're complicated. So what we had to do was called basis sampling, which is to write a scene generator you can use geometric error, you can use algebraic error, and you try to find the basis that gives you, generate different bases, and to find out which one will give you the most stable solver. And the way you can measure that is just what is your algebraic error on the constraints, or we also use geometric error, but it doesn't really matter. So there is sort of like a sampling over polynomial solvers that we did, because there wasn't much we could do to simplify these constraints. So for the journal version, we were thinking like, well, what could we do to try to actually, we even tried this for the original paper. I mean, it was just too much though. I had these constraints for the original paper, but the idea was that we don't want to just use this as a black box. We're going to try to simplify these solvers much as we did with the radial distorted conjugate translations and the meets of join solver. So what if we linearize the rectifying transformation was the question. What if we try to do this? And the idea is that we want to use the change of scale due to the imaging. So instead of looking at this direct encoding of scale, can we see how the transformation, if we linearize it, what this change of scale is, which is represented in the Jacobian of the linearization of the rectifying transformation, and in particular the determinant of the Jacobian. So the idea was that hopefully this linearization would simplify the solvers. And what you see on the right there is the change of scale for a particular scene plane, imaging with scene plane. So this encodes the change of scale not only due to the rectifying transformation, but also due to the undistortion. So you can see that like this is some relative scale change here, which is given by this Perula color map that is measured by these constraints that I'm talking about. There's some relative point that we choose, like in the middle of that image, that we select to be sort of the unit scale. And then you see the change of scale due to the rectifying and undistorting transformation. And on the bottom, of course, you see that there is a larger relative change of scale, and on the top is smaller. So like when you rectify, as you've seen in these prior images, the idea is, well, as a rectification maybe here, the idea is that when you perform this rectification problem, it's changing the scale of the image locally to perform that rectification. And that color map is representing that change of scale. And these functions, that this is what's represented by these set of equations here, which is we write out this transformation. So and now we're not dealing, so now there's this solver is in inhomogeneous coordinates. Now we deal for the first time in image space directly. So what I'm writing here now is X bar is now no longer a homogeneous coordinate, but an inhomogeneous coordinate. And we write out the rectifying transformation. It turns out, interestingly, that it's radial. It's not radially symmetric, but it's radial, which I think is something that can be exploited that hasn't really been exploited, but that's another topic. So that is the, on the right of this first row, this X tilde divided by L transpose, and F is the, L transpose is the vanishing line, and F is the undistortion function. And okay, and I have mixed notation here, and I'm sorry about that because you can't really see it in the fonts here, but in fact, those are homogeneous. The denominator is homogeneous, but the coordinates are inhomogeneous. There's not a better way I could do it, sorry. But you can see that that's the, on the right are the Euclidean coordinates of the rectified point and undistorted point. And what we do is we linearize this transformation, just by taking the first order approximation. And you can see the Jacobian falls out there. It's a function of L and lambda. And then we capture the change of scale, which is the determinant of the Jacobian. So we have then this quantity is what we can use, because we have the scale of the rectified point, which is this SI underbar, and we have the scale of the distorted point. And we know that when you apply that locally, the change of scale to whatever the scale is in the distorted region, it must equal the rectified, because you're locally changing the scale such that that constraint holds. Is it clear what I said? Maybe it's, I mean, so this one's a little bit involved, but maybe there's a question on it. Well, regardless, like the local affine frame is a region. It gives you a measurement of the distorted scale, right? Because you have this triangle, so to speak, one of these measurements, like I've shown here, these triangles here. So that's giving you, for example, on the left in these images, a distorted measure of the scale, because I can take the determinant of that, right? And so that's SI tilde. Now I need to change that scale such that it equals the rectified scale. And where the constraint comes in is we know that if these repeats are in correspondence, their rectified scales must be equal. And so that's the bottom equation. And now we have a linearization of this problem.
So I and J, these correspond to what?
These are features. So that's one of these triangles, a measurement. So S tilde I is a measurement from an affine-covariant region on the distorted scale.
For example, Y corresponds to one triangle and J to another one.
For example, yes. And these are in correspondence, though. We know that, I remember we talked about corresponded sets. So we can put these in correspondence. We know that after rectification, because of the affine invariant, that rectified scales must be equal. So now we have our constraints and we can plug that into a solver generator. And I thought, okay, hurrah, we've linearized it, it's going to be simpler. I'll get to that in a second. So this is the change of scale. So this is a summary of all that. So again, we have the same configurations. We know this geometric invariant is the same, that they must have the same affine rectification scale. Those are our minimal configurations exhaustively, 2, 2, 2, 3, 2, and 4 for unknown division model parameter and vanishing line. Those are unknowns. And on the right, you have some results, and you have this perula color overlap of the image that shows the change of scale due to imaging, which we can also compute now because we have it measured. So this is essentially plotting that determinant, that perula color map.
Maybe just a small question on notation here. When we write J sub X bar in parentheses L and lambda, to me it's not particularly clear here with respect to what variables we take the Jacobian.
With respect to the measurement, that's why.
I see, but
or
don't you think that somehow the notation must be changed? Because when I write vertical bar and I evaluate it is at X tilde and Y tilde, only after that it becomes a function in L and lambda only. But before it was a function in X tilde, Y tilde, L and lambda.
Yeah, I mean, okay, well, possibly there's a better notation. Let's maybe just, so you're suggesting that, what is your solution then? What would you prefer to see there?
Maybe in front of L and lambda, right? X tilde and Y.
I think I only wrote X bar there to show that it's the Jacobian of the function X in terms of this rectifying function in terms of the measurements. Like this del X tilde del Y tilde, for example, that's sort of a perturbation of the measurement. Where the point where the scale is being measured, you have to have some point around which the scale is measured, which is the origin of that affine basis, and that's what we are perturbing there. Okay, you just have a problem with the notation.
Notation is always difficult. I think we understand that we differentiate with respect to X and Y and substitute XY to Y. rectifier, then you look at it. So I think that's the way.
That's right. And then you, those are your,
You have it somehow sloped, right? Okay, but I think yeah, this is hard to visualize. And having shown, right?
but I think that what was nice is that we all understand. Okay, so I was really happy about this and that we could do this. And in fact, this was the state of the art. Had sort of the first set of solvers was not tried before. The state of the art had a change of scale solver, of course, not for lens undistortion and rectification, but for fine rectification. And Andra Home had done it, and then prior to that, I think Cremonesi had done it, although he didn't use affine-covariant regions, and that was the novelty that Andra introduced. But it didn't matter. Linearization didn't matter. They're equally complicated. Template elimination template the same. Nothing changed. So somehow it didn't help at all, which was a surprise. So unlike the first example, this was okay. We put it in the journal. It's nice that we have another set of solvers, but in reality, there was some empirical differences. Actually, the change of scale solvers did happen to perform slightly better for some reason, but it's not obvious from the. Now, what if we take a look at all these solvers for different problems? Like, what did we achieve from these solvers? This is a simulated experiment with noise and outliers. And there's a bunch of, okay, I have all this notation here because we have so many different solvers. But the takeaway is the black guy, H2L lambda, the black line contour, is the meets of joins solver, which was the half microsecond solver. And you can see that it's, and this is not based on correspondence, right? Because all, like, there are other one correspondence solvers here. For example, if I look at H2LU lambda, this blue guy is also one affine correspondence. But it performs the best because it's simple, there's no elimination template, and it's not sensitive to noise. You can see that the second best solver, surprisingly, is this pink guy, which is this, actually that's that directly encoded scale solver. So the change of scale, or the directly encoded scale solver, the first solver, which is that determinant constraint that I showed first, it's performing second best, even though it requires more correspondences than some of the conjugate translation solvers. So that's showing that the conjugate translation solvers, because we had to use Grosvenor basis, are sensitive to the noise. So, you know, and generating trash sometimes, or a lot of the times. So it just goes to show how important it is to test the sensitivity, to look at different solver designs. Yeah, so that's just sort of a comparison. Okay, now we've gotten to the affine rectified space. What about the metric upgrade? So we are given an image, for example, here's a rotational symmetry. It could also be an isometry for the metric upgrade. And the idea is this, like in the affine rectified space, so this is after we remove the distortion and do the affine rectification, and affine invariants are restored. We have a geometry that looks like this. The idea is that we can take our affine covariant regions, remember these triangles that we have, treat them as free vectors, translate them so that they have a common origin, and construct these ellipses. And the point is that if we restore, we know that the extents of these affine covariant regions, since they're repetitive patterns, they must be congruent. So we would like to restore the congruence of these extents. And that's exactly what we do to get the metric upgrade. So we apply in a global, now, by the way, the difference now is that there's a global transformation that restores the metric rectification. The other transformations were local. Affine rectification was local and lens undistortion, but this now is a global transformation on the entire image that that restores. And yeah, so what's the algebra? You have an affine transformation that takes the ellipse to a circle. And we know that so when you do that, there's a radii that's associated with one of these extents. So this for example is for one constraint, and we stack these. So we have the unknowns, which are the affine transformation ABC, and we have these unknown radii, although we know that they must be equal for corresponding extents. We solve the system of equations and then construct the sigma. We recover the sigma matrix. Sorry, it's the vice versa. We recover this sigma matrix, which is this positive semi-definite matrix that has this property. And we know that when we write those constraints down and we enforce that these radii must be equal by using the same unknown, it's unknown but equal, then we can recover this sigma, and then we can use Cholesky decomposition to get the affine matrix that we need to metrically rectify. So, and those are the unknowns. So you have three unknowns for this sigma, which is encoding the affine transformation eventually, and then one unknown for each radii of a correspondence. So like if you have 3 repeats, there's only one unknown introduced because they all have the same radii in the metric rectified space. So that's our metric rectification. And this is, now we have a reflection. So again, we're in the affine rectified space, something that looks like this. By the way, this is a long focal length image, unfortunately. So, okay, but whatever. But so the perspective image looks a lot like the affine rectified image. But now we have the semi-metric rectification. So we have, again, our affine-covariant regions. We treat them as free vectors, translate them to a common origin. And we know that now instead of, we use a point coincidence relation. We know that there's a reflection axis, and that when you reflect about that axis, these points must be coincident. And that's what's modeled here. The reflection taking one point on top of another. And X prime is our metric rectified point. And then we introduce this A, which is our unknown semi-metric rectification, and solve these system equations, which is this incidence equation, also linear. So both of these are very fast because both metric and semi-metric are linear upgrades. So we have all that. So now we can go backwards, right? Like all of that stuff that we did on all these different configurations and metric rectification and semi-metric rectification, this pipeline, we can go from the right side, which is the image, to the undistortion and to a rectification. So on the left side is the rectified space. And how to design a maximum likelihood estimator because now these are all minimal, right? Like we have minimal samples, we've ransacked, we have these models, and now we need to refine these somehow. So because it's still not very good, because we want more measurements. Some of these estimates are computed from just one correspondence, or once you do the upgrade too. So it's going to be quite noisy. And the idea is that it's like structure from motion except for patterns, and it's actually a difficult problem. In that we basically in the rectified space, we reconstruct the pattern. So we had to choose some representation for it because printing out a symmetry is not unique. So we print the pattern in rectified space. This is hard in itself because it's a model selection problem. What is the minimal representation for all of these repetitive patterns? How do you print them out? It's actually very difficult, which I spent a lot of time on. And then you have, so you reconstruct in this rectified space, and then you print it. And by printing it, I mean projecting it back into the image. And that's where you measure your error. So now you're dealing with the image noise where you want to be in the image space, and you have a maximum likelihood estimator, nonlinear least squares. Okay, run your Levenberg Marquette, and you get something better, hopefully. All right, so that's that work. Now we go on to the complementary features. So the idea here is like we have all of these nice solvers for affine-covariant regions. What if there are scenes that don't have a lot of texture, right? The affine-covariant regions are good where we have repetitive texture, but there's going to be scenes that could have very little texture, and we may not get a lot of correspondences. It happens a lot. And so the idea of the work was, let's combine it with imaged lines or parallel scene lines, for example. So we want to take these different configurations and combine them in ways where we can solve a larger class of imagery. And we have two challenges, right? Like circular arcs in the image space under the division model of lens distortion. Circular arcs are hard to group as image parallel lines. Why? We don't have a good descriptor for them. Okay, that's changed recently, right? Because many people have started designing line descriptors. I know Victor Larson's doing it, for example, his group, they did some stuff, but circular arcs are hard to group because of the correspondence problem. And covariant regions are noisy, so they provide less accuracy. So can we combine these two things? And so can we use both to sort of remove the disadvantages of each feature type? And here's some representation of our measurements now once we have these complementary features. So here we have Manhattan directions shown in red, green, and blue. A Manhattan frame, by the way, is simply a fancy way of saying a orthogonal coordinate system in the scene. And in fact, when you compute the camera geometry, it's the origin. It's just a basis. So you treat it as such. So what we have on the left is the image parallel scene lines. So if we use a line extractor or circular arc extractor, because this is under distortion, if we use a circular arc extractor, we get on the left side those measurements. If we use a affine covariant region detector, is what we get on the right. And what I've done is for the affine covariant regions, those triplets of points, I've showing their joins. So this is, you can see that they give different types of measurements. And how can we use that? Well, there's two cases, like if we don't know this a priori. So again, we're looking at the configuration of the image vanishing points. In the scene, there may be, or in the image, there may be 3 distinct vanishing points that you can measure. So I'm showing those constraints there. If we don't know that there are, so we have 2 sets of unknowns based on the scene configuration on one axis, on 2 axes. On the first axis, so the x-axis, we have the number of vanishing points. Are there 2 or are there 3? On the vertical axis, we don't know the configuration of those vanishing points in the scene. Are they just coplanar, or additionally, are they orthogonal as well? We don't know. And that will determine the type of geometry that we can estimate, but a priori, we don't know. So the idea is that for coplanar 3 distinct vanishing points, we have the constraint on the top left. For orthogonal, we have an additional constraint, which is that when we have this image of the absolute conic, we can the vanishing points must be orthogonal. So that's the equation what's representing now. So the first equation is the incidence of vanishing points and vanishing lines, and the second equation is showing the using the image of the absolute conic, which we parameterize only as a function of the focal length, that these are orthogonal vanishing points. And then we have the case where there's 2 distinct vanishing points only, which we don't know a priori. And in that case, we had added an additional constraint that we treat them as 3, but we add this additional constraint that they must be, 2 of them must be coincident with this cross product. So this is what we add into the set of equations. So how do we use all this? And what are our different configurations? Well, as I showed here, maybe I'll emphasize this again. These vanishing points can be constructed from meets of joins as before, and we can get our meets 2 ways. We can use directly the circular arcs, or we can join our affine covariant regions, and then we can use all of these constraints. And so that's what's being shown at the top, how to construct these meets of joins. This R2P4C is, for example, 2 points and 4 circular arcs, and 2 point correspondences, I should say, and then 4 circular arcs, 4 points, 2 circular arcs, 6 circular arcs, and 5 circular arcs. These are the different configurations that we are sampling. So we don't know which one of these is valid, essentially, how, if there's 2 vanishing points, if there's 3, or what kind of content is the scene. So what we do is use what's called a hybrid ransack. And all this means is that ransack now has multiple solvers to choose from. And it dynamically tries to pick which solver is the best for the configuration in the scene. So, and it's using the inlier sets, the consensus sets, to sort of find out which solvers are performing the best from a group of solvers. So now we're using all of our solvers jointly to try to solve a scene, which allows us to solve a wider variety of the scene. And what is the output of this hybrid ransack or this estimation process? If you have orthogonal vanishing points, you get the lens undistortion parameter lambda, you get the focal length f, and you get the absolute orientation of the camera with respect to the Manhattan frame. So this is an example of the scene parsing. You've seen this figure before. This is a result of this method. You get the vanishing point label, the vanishing line label. You can label the circular arcs where which vanishing point they belong, the affine-covariant regions, which vanishing line they belong to. You can do the rectifications, and you can do the undistortion. And you get metric, by the way, there's no upgrade here, by the way. Metric rectification here is direct because you're directly computing this rotation. So you know the calibration and you know the rotation, so you can directly get the rectification. So this is a direct shot. There's no hierarchy here. Here are some results. This is Manhattan frame rectification. You have inputs on the top left, and then on the bottom left, the cutout is distorted, and then the 3 Manhattan planes are rectified on the right. And it's an impressive result, I think, because if you look, for example, at this little bike guy on the bottom right, this bicycle guy, you look in the image, the kind of distortion that's experiencing, and we can completely remove that. High accuracy. This is showing the different solver configurations, and what the idea of this graph is that we had a data set called the AIT data set. It's a standard data set for auto-calibration of distorted images. It was introduced by Wildenauer. I should put a reference there. And the idea is that which of these solvers gave the best, how often did these solvers give the top solution, is all it is, the best solution. And you can see that because of the different configurations of the features, some solvers solved certain images better, certain types of images. And so really this motivates the use of hybrid ransack or some sort of ransack that takes all solvers into account so you can solve more images. I think this is just showing that once you combine all solvers, which is on the right, this, I don't know, color pink, it's giving the best performance on different metrics. Like these are empirical CDFs. So you have relative error of lens and distortion parameter and relative error of focal length. And these empirical CDFs are showing the percentage of time so that the error is below some threshold. And I'll get to this green line in a second. We'll come back to that. I wanted to show you the difficulty of this problem, which is disentangling focal length and lens undistortion. And this actually is interesting because it ties into Victor Larsen's talks, which was at the last algebraic vision meeting about radial cameras. Focal length and at least radial lens distortion are acting radially along the diameter of the image or the radius of the image. So they're very difficult to disentangle because one parameter can account for the error of the other. And that is what this is showing. So we have on the x-axis here, we have the signed relative error of lens undistortion, and then the signed relative error of focal length. And of course, here we have in the middle the warp error, which I introduced a long time ago, which is this pre-imaging and imaging method of error. And of course, in the middle, you have the lowest error where both parameters are correct. But you can see along the diagonal that one parameter is accounting for the error of the other. So this is a very non-convex problem, very non, but it's a difficult problem. And this is a figure that sort of motivates why it's difficult to disentangle these two. So now I'll talk about some of the challenges of using affine-covariant. How much do I have? 5 minutes, okay. So reality check, I don't have much time left, is the reality check. But I'll talk quickly about some actually work that Thomas and and I think Victor will maybe jump on as well, that we're doing with respect to correcting or using affine-covariant regions. So back to the performance, if you just, for auto-calibration, if you just use affine-covariant regions, not using circular arcs on this AIT data set, which is like 100 images of lens distorted images, you can see the green line, which is using only these covariant regions. And if you look at the error, the performance is awful, really bad. And the reason for that is that they're noisy. They're extremely noisy. And this is a known problem, as we discussed, for two-view geometry estimation as well. Something has to be done to make them useful in general, to make them useful only as a feature by themselves. They have to be corrected somehow. Either, you know, there's something needs to be done to use them directly in the solvers. So a little bit of motivation is that if we look at this affine transformation, which takes us from the canonical basis to the affine basis, the top left of this guy is controlling the shape of this affine basis, these 2x2 parameters. That's really like manipulating. If we assume that the location is correct, then that's really what's changing the shape of the affine basis. And we can take a look at the Frobenius norm of this upper 2x2, and it characterizes the geometric error directly. I mean, it's an algebraic measure, but it's actually characterizing the geometric error. And what my colleague did here was to print, it's very difficult to see here, but these tensors, these matrices, are these upper 2x2 elements. And you can see the difference between these upper 2x2 elements for these patches. And these patches are affine covariant regions extracted. And you can see that their normalization is quite good at the bottom. Like they look, after this transformation to the canonical frame, pretty darn close. But in fact, the upper 2x2 is varying quite a bit, which is this normalization. And this is what needs to be worked on for these features to be used in practice. And to give some perspective, like for reconstruction pipelines and single view, for reconstruction pipelines or auto-calibration, these features are not used, even though there's been tens of thousands of citations generated by them. So definitely work to be done if we want to use those. I just wanted to quickly go through the prior work, now that you're familiar with some of these concepts. Fitzgibbon at least it was one of the first to use the division model to model lens undistortion. That's been used throughout all of these minimal solvers. Shafalitsky was the first to design solvers for conjugate translations and use them for repetitive texture detection. Holman Matas used the first use of affine covariant regions for this change of scale type of formulation that I introduced, or I talked about. Ota et al. Was actually the first I know in computer vision to use this change of scale constraint from quite an old paper. And Cremonesi also used this constraint too. So there's 3 papers about this change of scale and affine covariant, restoring this affine invariant of equal scale. And in terms of using sort of the formulation that was used for the radially distorted conjugate translation solvers was inspired by Susanna Kokeleva's work on the radial distortion homography. And this is the biography for all of the novel work that has been presented in this tutorial. And then I'm done. Do we have time for questions, or do we not have time for questions?
We would have like 1 minute time for questions, but are there any more questions?
I don't know, maybe if there's none on Zoom, then there's none. Yes.
Let's start. Okay, thank you.